All right, so we talked about breaking down peptides. Now let's talk about building them up. And like most things in organic chemistry, it's named after the guy who figured out how to do it. So we're going to talk about the Merrifield solid phase peptide synthesis. And there's two kind of things you need to worry about here. What is this solid phase? And then how do we activate the carboxy terminus of one of the amino acids to get it to bond to the N terminus of the other? So it starts with a polystyrene divinyl benzene polymer. So you have a phenyl group and then a CH2. So polystyrene would look like this. And then you've got another phenyl group. And then a CH2. And then you keep going. Okay, so it's polystyrene, which is a polymer of styrene. Styrene is simply vinyl benzene. So you'll notice that your repeating unit is here, right? Phenyl CH, CH2, phenyl CH, CH2, multiple polystyrenes. And it's usually cross-linked with 1 to 2% divinyl benzene, which is basically just styrene with an additional vinyl group on the end. And what that does is give you a three-dimensional polymer instead of a two-dimensional polymer, so it's not just a straight chain, because some of these can support chain formation on both sides. What you're trying to do is you're going to try to control the pore size of your polymer so that you can control how much it swells when you put it into solvent. That's not reactive. So the first step is chloromethylation. Using a really nasty reagent. Chloromethyl methyl ether. And a Lewis acid catalyst like aluminum chloride or ferric chloride or some other Lewis acid catalyst. And what we're going to do is we're going to take some subset of those phenyl rings. So we'll just ignore the rest of the polymer and put a chloromethyl group on there. So what's the mechanism of that reaction? This chloromethylation of our polymer. If you were asked for the mechanism, what would you do first? We're substituting on a benzene ring, and we're taking off a hydrogen, we're replacing it with a chloromethyl group. So what class of reactions does that look like it probably fits into? Substitution on a benzene ring that didn't have a leaving group attached. Probably it's electrophilic aromatic substitution. Because we don't have a strong base, so there's not going to be any benzyne intermediates. Right? It's not a pyridine ring, so there's no Tichy-Bobbin reaction. Can't be ipso without a leaving group. So then the question becomes, what's the electrophile? So so we just change the question. Hopefully, if we change the question, we eventually get to one we can answer. You could also approach it by, if we take chloromethyl ether and stick it in the presence of a Lewis acid like aluminum chloride, how is that likely to react with aluminum chloride? So you might think that the chlorine is going to attach to that, because that's what happens in the Friedel-Crafts alkylation and the Friedel-Crafts acylation. But who's more electronegative, oxygen or chlorine? So which one has the larger partial negative charge, oxygen or chlorine? Oxygen. So I drew the aluminum right under the oxygen because it's the oxygen that's going to attack it. That's your electrophile. We've activated this oxygen so that it can leave, and now your benzene ring is going to attack this carbon. And break that bond. So it's similar to the Friedel-Crafts reaction. I don't really need to draw the rest of those. But it's not exactly the Friedel-Crafts reaction because it's an oxygen that's being activated instead of chlorine. That puts that CH2Cl group on there. All we need to do is pull that proton off, and we can use this pair of electrons to pull that off, generating the chloromethylated product and methanol, and regenerating our catalyst. So it's an electrophilic aromatic substitution. It's not that different from what you've seen before with the Friedel-Crafts alkylation, just a different looking electrophile. So what we have here is a benzylic chloride. And those react readily by SN2 pathway. So we can displace that chlorine on our chloromethylated resin using the C-terminus of a protected amino acid. We have our negatively charged carbonyl group. We have our R group on there. And we have some kind of protecting group on the nitrogen. And we'll talk about what that protecting group is in a second. So we have a nucleophile, the C-terminal amino acid. We're going to come in here and do an SF2 displacement. We will have successfully anchored our carboxy terminus. So we have an ester link, right? There's an ester here that anchors C-terminal to the polymer. It's important that you have a protected amine terminus because the amine terminus is nucleophilic, better nucleophile than the carboxy terminus. So if you don't have a protecting group there, you're actually going to get your N terminus and your C terminus both binding. You'll get a mixture of products that's pretty useless. The nice thing about solid phase synthesis is you don't purify things in between because your peptide, as you start building, is attached to the polymer. So you can wash away excess reagents and byproducts by simply sticking this in a column and flushing solvent through until all your byproducts are gone. That allows you to use large excesses of reagent so we can get a high coupling yield without having to worry about the fact that you've got a lot of excess reagent to purify away. So what do we use as a protecting group? What kinds of things are used to protect the N terminus so that it won't react and again, when we protect the N terminus, we're going to be working with the -1 species of our amino acid, which is always at equilibrium with the deuterion. The nitrogen is a better nucleophile than the oxygen, so we can get the nitrogen to react. And there are 3 common reagents that are used for protecting that N terminus. One of them is that. The other one looks like that. And the third one looks like this. This is benzyl chloroformate. This is dicarboxyl dicarbonate. This one is 9-fluorenyl methyl chloroformate. A chloroformate simply has an OR group on one side and a chlorine on the other side. So here we have a benzyl group. This is a 9-fluorenyl methyl group. And then the chloroformate part is the OC double bond OCl. This is a dicarbonate, right? We've got a carbonate link on both sides. All of these are good electrophiles that are going to react with a nucleophile by nucleophilic acyl substitution. So which one would you like to react with that NH2 group? I think if you know one of those mechanisms, you know them all. So let's use this one. Yes. So we do a nucleophilic attack on our carbonyl group. We have our amino acid. Our leaving group. And then someone takes that proton off. So some base comes in. Probably not the chloride ion. Probably something else that's present in solution. We'll just write it as B. Base. So we now got a protected amino acid. That'll end up getting protonated And so you can buy these. And this is what's called a CBZ group. Or sometimes just abbreviated Z, stands for carboxybenzyl. This is the carboxy part, and this is the benzyl part. The important thing to notice about this is that it is a carbamate. All of those will be carbamates, which is a carbon-oxygen bond in between a nitrogen and an oxygen. So you can protect your amino acid as either a CBZ group or alternatively a t-butyloxycarbonyl, which is abbreviated BOC. There's the t-butyl part, there's the oxy, and there's the carbonyl. So t-butyloxycarbonyl is BOC, or a 9-fluorenomethyloxycarbonyl, which is also known as FMOC. We don't have to write out 9-fluorenomethyloxycarbonyl all the time. So just FMOC, there's the 9-fluorenyl part. This is numbered like this. So the methyl group is attached. So it's 9-fluorenyl. So 9-fluorenomethyloxycarbonyl, but they're all carbamates. They're all purchasable. You have to be a little bit careful with this because it disproportionates to form the carbonate and phosgene gas, and phosgene gas is toxic. Those are just nucleophilic acyl substitution reactions. With the diterbutyl dicarbonate, the leaving group isn't chloride, the leaving group is an oxygen anion. So we can buy these. Or you can make them. So now what we have is our polystyrene with a C-terminal amino acid attached to it, an R group. Okay, and we've got an N-terminal amino acid that's protected with some group. Let's use BOC because it's easy to draw. So this is a BOC-protected N-terminal amino acid. So what we need to do now is we need to take that protecting group off. To free up the N-terminus for reaction. And the reagent that's usually used to take the BOC group off is trifluoroacetic acid. To take off the other groups, there are different reagents. So to take off the CBZ group, the reagent that's typically used gas and a catalyst, platinum oxide, for example. And the other products are toluene, CO2. In this case, the other products are CO2, butanol. And to take off the FMOC group, different reagent. Reagent for taking off the FMOC group is piperidine, like pyridine, except that it doesn't have the benzene ring. And same thing. Generates the free cane and also generates CO2. So what kind of mechanisms are we probably talking about here? Trifluoroacetic acid takes off the bot group. Hydrogenolysis takes off the CBZ group. Piperidine, which is a base. So it's nice that Bach is cleaved by acid. FMOC is cleaved by base. CBZ or Z is cleaved under neutral conditions. Recall that lysine actually has an NH2 in the side chain as well as the N-terminus, which you'll need to protect so that the side chain doesn't react. The nice thing about having 3 different protecting groups that are cleaved under different reaction conditions is we can do what's called orthogonal protection, where you protect 2 things with a different protecting group, and you can take each one of those groups off in the presence of the other. Yeah. So mechanistically, how do you think these guys work? This one, it's kind of poof. Right? We know that benzylic ethers, this is a benzylic ether here. Or actually, benzylic esters. Right? Benzylic ethers or esters are cleaved by hydrogenolysis by just adding hydrogen across this bond. So we can add hydrogen across there. One hydrogen goes to the CH3 group to form, or CH2 group to form toluene. The other goes to the carboxylic acid. But that's unstable. Oops. Got the NH in the wrong spot. This is a carbamic acid. And you probably remember from the Hoffman rearrangement that carbamic acids are unstable and will spontaneously liberate CO2 and uridine. So that's exactly the same thing that happens in the Hoffman rearrangement. So that one, there's no mechanism, that's just poof, right? Hydrogen adds across that bond. And it adds across that bond because it's a benzylic position, and only if it's a benzylic position. But what about the other two? What kinds of mechanisms are we talking about? No, not at all.
Like with the Fisher esterification, like that class of things, except I can't remember what it's called.
Fisher esterification is a nucleophilic acyl substitution.
Yeah, that.
So we should protonate something. What should we protonate? Great Rule of Organic Chemistry number 1. Probably this carbonyl oxide gets protonated. I'm just going to write this as R. Doesn't matter what's attached to that age group. So we're protonating the carbonyl. There's a resonance structure for that that looks like this. And t-butyl cation is super stable. So it simply falls off. To generate a carbamic acid and a tertiary stable cation. This carbamic acid now decomposes the same way all carbamic acids decompose to generate CO2 and generate the N-terminus. So the reason it works for Bach is because of the stability of the t-butyl cation. And then that t-butyl cation is going to get trapped by water or something else that's present in there. Eventually become t-butanol. So that's simply an acid-catalyzed reaction, but it's a little different from your typical acid-catalyzed hydrolysis in that the next step is not this carbonyl being attacked by water. Because you've got that t-butyl group that can fly off spontaneously as the carbocation, you don't need the 6 steps that you would normally need in the Fisher esterification. All right, so t-butyl cation stability, that's the key behind the block protection. What about FMOC? What's the key to success for the FMOC? The key to success for the FMOC group is this is doubly benzylic. Which means this is very acidic. Pyridine is going to grab that hydrogen and it's going to go into E2 elimination. It's going to generate that product. It's going to generate the dibenzylfulvene. And it's going to generate that. And then you'll regenerate your piperidine by deprotonating that. So the thing that makes FMOC effective is the presence of an acidic proton in that 9 position of fluorine. And it's acidic because once you take that off, if you were not to do an E2 elimination, if you were just to take that proton off, let's just say that, we look at this stepwise, we take that proton off and we don't spontaneously cleave off CO2. What can you tell me about that anion? That's the 9-fluorenyl anion. I said that was very acidic, which implies that this is very stable. Why is that anion so damn stable? In fact, it's stable enough that dibenzyl fulvene, once you're formed, is actually going to react with piperidine, or can react with piperidine to do this. Make that anion. And then 2 proton transfers will actually generate a byproduct. If you're doing the synthesis in solution, this byproduct is a pain in the ass because it's hard to get rid of. But if you're doing it in solid phase, that doesn't matter because it's not attached to the solid phase, which means you can flush it out by just rinsing with solvent. What's so stable about these anions here that makes them form? Oh, no, not here. Here they should be. That one's protonated. So this is aromatic, right? It's 4n plus 2, where n equals 3, 14 pi electrons. So that 14 pi electron aromatic anion is so stable that it makes this hydrogen acidic enough to be removed by a relatively mild base, right? Piperidine is not normally a base that you would associate with an E2 elimination. It's not that strong, but it's strong enough to take off this super acidic proton. So we can take off the protecting group and generate a free N-terminus attached to a solid phase. And next week, Thursday, we will talk about the rest of it, which is now how do you activate the carboxyl group of another amino acid and get it to react with that N-terminus.